Alright guys, so in our last video we started talking about leading coefficient tests and we dove into how to determine n behaviors. Well, in this video we're going to take it one little step further and we're going to think about a concept called multiplicity. Alright, multiplicity. And that relates to what we talk about with repeated zeros, in which a zero or an x-intercept or a solution to a polynomial function, alright, there is more than one of the same solution. Now, it doesn't mean that it necessarily crosses over at x equals 1, for example, multiple times. What this shows is that it's the same zero happening multiple times, hence the multiplicity of it. So let's say, for instance, you make a factor of a specific polynomial, and you get that it's x minus a to the k power. So k is a number of times that x minus a was your actual factor for the polynomial. We know we factor it out, set equal to 0, well that's when we have a 0. And so when it happens more than once, that's when it's called a repeated 0. And so here's some more interesting facts about it. If your multiplicity k is in fact odd, the graph crosses the x-axis at x equals a. Crosses. Notice the we'll talk about number 2, and then we'll talk about the difference. Then if k is even, the multiplicity is even, then the graph touches the x-axis, but does not cross at x equals a. Take a key difference here. What do you notice? The graph crosses the x-axis and the graph touches the x-axis. Take a moment. Answer this question to yourself. Why is this important? What does it mean for it to just cross or it to just touch? What is really the difference between these graphs? Hopefully, you can see that when a graph crosses, we are completely changing the sign or the values for our y or our f of x or whatever of x function that we are dealing with. We are going from the positive to the negative, or the negative to the positive. This is going to be crucial when we start diving on into derivatives. Now, well, if it's just going to touch it, that means that there's no real sign change in y. There's no sign change in y, right? If that vertex of the parabola is on x equals a, and it's a positive leading coefficient, that just simply means that every y value is still going to be positive, right? Or if it was flipped on over and it was negative x squared, that means all of those positive x's now just become negative because you have that opposite approach on in there. So, how does this kind of relate in terms of something you need to solve for? Take a look. We're going to go ahead and actually take into account determining the multiplicity of each of these. So it can be said for a polynomial function of, we're going to call it f, of degree n, that the following is true. Well, the graph of s has blank. N what? What do you think? N what? Well, hopefully we kind of understand that if it's going to have a degree of n, what's the total number of turning points or the changes of directions that it can have? Well, it's n minus 1 because the total number that it could have is 1 less than the degree itself. Remember, that goes back to talking about our actual turns and twists and everything changes from that degree itself. Well, what also can be said about it? Well, the graph of f also has at most what? The graph of f, the degree of n, can have at most what? Well, hopefully you know that the degree actually gives you the amount of solutions that can have. So if it has degree 2, and it can have at most 2 real solutions. If it has degree of 8, it can have at most n or 8 number of real solutions or zeros in this particular case. All right, so now let's talk about zeros of a polynomial, and let's dive on into looking at multiplicity. So the following example says find all the real zeros of the polynomial and determine the turning points of the graph, or the multiplicity of the graph itself. All right, so let's take a look here. So in this example, we want to go ahead and factor on out what's in common. So I'm going to go ahead and sorry guys, my microphone fell on off, but let's dive right back on in. Find all the real zeros of the polynomial function and go ahead and determine what the multiplicity of each is. So let's take a look here. So if we're solving for the zeros, the number one thing is we want to find out what the factors are. So these factors on equal to 0 itself. So what's in common? Well, what I notice is that there's definitely a 2 in both of them, and there's also an x in both of them, but not just an x, but there's 2 x's, so there's an x squared that we happen on each. So I'm going to go ahead and just pull out a negative 2x squared. Usually it makes it just a little bit easier for us. And then what are we left on with? We have x squared minus 1. Okay? Well, this also helps me understand that negative 2x squared, this x squared minus 1 can factor out one more time. I mean, this is a difference of squares. And so now we have x plus 1 and x minus 1. So there's our 3 factors that we have on in there. And so if we set each of these equal to 0, we know that x equals 0 is 1, x equals negative 1 is a solution, and 1 is a solution as well too. Okay. Well, this shows that the corresponding, in this case, right, the corresponding x-intercepts are at 0, 0, 1, 0, and negative 1, 0 in this particular example. So what if we were talking about, turning points specifically? Well, remember, we talked about that it can have at most n-1 turning point. So we know that it's going to have at most 3 turning points. So let's take a look and see if that actually was the case. And so we can maybe do a quick little sketch and say, hey, we know that we're going to have a x-intercept at negative 1, 0. We can do it again at 0, 0, and then at 1, 0 right in here. All right, and so something of the nature might look where you have it come on up, come back down, and then it's going to turn one more time and come back down there. And so you can see your 3 different turning points of it itself. All right, well, what about the multiplicity? Well, in this particular example, we're talking about multiplicity. Well, remember, none of them were repeated, right? So x equals 0 had a multiplicity of 1. X equals negative 1 is a multiplicity of 1. And then x equals 1 is a multiplicity of 1 as well, too. All right. So that kind of shows a little bit about turning points. Talks about what our zeros are. And specifically, we can relate that to the second point on here as well, too, where it says, hey, the graph has at most n real zeros. So the highest degree was 4, and so we kind of confirmed that it didn't have any more than 4 in this particular example. All right, let's take a look here. In our next one, we're going to go ahead and sketch this graph kind of like we did before. We want to go ahead and first and foremost look at what do we need. All right, so I've gone ahead and made 3 steps for us. We definitely need to use the leading coefficient test. Why? Because this determines the end behavior of the graph. Secondly, we gotta have to find out what the zeros are, because that's going to tell us when it either touches or crosses over the x-axis. And then lastly, we're going to plot some additional points to kind of help us make some test intervals here as well too. All right, so the graph that we're looking at here is 3x to the 4th minus 4x cubed. So first and foremost, let's take a look. The leading coefficient. So the leading coefficient is 3. So our leading coefficient is greater than 0. So it's going to be positive in this case. Okay? And now what about the degree? Well, the degree is even. So then we have to think to ourselves, what does it mean to have a leading coefficient that is positive and a degree that is even? Well, I'll step back out to our chart real quick just so we're kind of getting used to it. So once again, we have a degree that is even and a leading coefficient that is positive. So it looks like we're going to rise, and then we're going to rise again on the right-hand side for the behavior. All right. Step 2, we want to find the zeros and then go ahead and plot them. That's probably going to be the easiest thing to go ahead and plot first and foremost. So we have 3x to the fourth minus 4x cubed. Set that equal to 0. What's in common? Well, what I noticed is they have an x cubed in common in both of them, and so that brings us out to 3x minus 4 in here. So what does that give us? That gives us that we have x equals 0 and x equals a positive 4/3 in this case. And so we have x-intercepts occurring at 0, 0 and at 4/3, comma 0. So first and foremost, what I would do is go ahead and plot those ones. So we go ahead and plot those ones, and then somewhere in between 0 and 2, or 1 and 2, excuse me, we're going to have another one in there where it's going to cross. All right, so now we just want to go ahead and plot a couple additional points on in here to figure out what's specifically happening. Now, for me personally, I kind of use our plotted x-intercepts to figure out what's happening, because I want to know what the graph looks like to the left of 0, 0, in between 0, 0 and 4/3, and then after 4/3, comma 0 as well too. And so let's go ahead and make a brief chart. Okay, so we'll make a brief chart, and so I want to test somewhere from -infinity to 0. So let's go ahead and say, hey, let's test what happens when x equals -1, something less than 0. Well, if I were to substitute f of -1 into our equation in here, we end up seeing that we get -1 multiplied by -3 minus 4, so we end up getting a positive 7 in the end. So right here we have up here at about -1, 7. That's good, because we know that the end behavior on the left-hand side should be rising anyway. Well, what about specifically something happening on over about in between 0 and 4/3? Well, in between 0 and 4/3, let's take a look. So let's go ahead and, I mean, it's kind of up to you guys what you want to use. But what I always try to say is just choose some numbers that just make your life a little bit easier, if at all possible. So between 0 and 4/3, I'm thinking let x equal a positive 1. So we're going to substitute that positive 1 on in there, and substituting a positive 1 in there, we end up seeing that the value is -1, because you get 3 minus 4, that's our -1 right in there. And so we have a point on the graph now at 1, -1 specifically. And then what about at 4/3 and greater? So now you want to choose something that is bigger than 4/3 specifically. All right, so what about something bigger than 4/3? So our interval from 4/3 to positive infinity, let's make x equal kind of whatever you, like I said, anything bigger. You could use 2, you could use 1.5. I mean, it's something that shows still kind of what's happening on in there. Let's just go ahead and, I don't know, 1.5 is the last thing I said, so let's go ahead and say just 1.5. See what happens when you throw that on in there. So make f of 1.5. Substituting that on in, let me pull my calculator out real quick. All right, and that's going to end up getting us about 1.6875. Probably should have used 2. That would have probably been a little bit easier in there. So you could use 2 or 3. Honestly, anything bigger than 4/3 would have been just fine as well too. So, and then somewhere in between here, you've got our positive. All right, guys. So the only thing that I'm going to caution now, because we do have some points here, and it would be very just kind of easy to go ahead and connect those dots, I guess, specifically to each of them. But also kind of remember what some of the, different turning points and things could end up being in our example. And so remember, we could have n-1 turning points, okay? And because there is a possibility for more turning points in there, you're probably gonna have one. And so what I want to make note is that a graph like this, and you're gonna start to kind of notice as you get a little more practice with it, is gonna actually start to make a turn here and then come back on up. So in some examples, it may be even a better opportunity to choose something else also maybe in between 0 and maybe a half, and see what else is changing in there. Because remember, the concept of just touching our x-axis or physically crossing on over the x-axis as well too. All right, guys. So as we kind of wrap some things on up, I've got one to try on your own. Once again, guys, don't forget the steps. Go ahead and find that leading coefficient, find the zeros and plot them, and then find some intervals that you can work with that are going to be to the left of that last x-intercept, in between the x-intercepts, and then find out where it's going to rise or fall. All right, guys, give this one a shot, and we're on to the next one.